Hello everyone and welcome to Atoms and Sporks, and today I want to talk about the fundamental limits of conventional computing. So to start things off, I'd like you to take the computing device you're watching this on, be it PC or smartphone or game console or whatever, and just rip it open. Just tear it right open. I'll wait. Okay, now what you'll now see is one of these, a printed circuit board or PCB. We don't care about this. All we care about are these little gray boxes called packages. Now take one of these and rip that open, and you'll find this, a solid hunk of silicon called a die. This whole thing is a single integrated circuit, the entire basis of our computing technology. Now take this little guy out and just rip it in half, go on, and put it in your handy transmission electron microscope. You'll see something like this, which schematically can be represented something like this. Now, all this top stuff is actually just interconnects. It's like a complicated highway system of like little embedded wires that connect devices to each other. We don't care about this. You can rip them off. Rather, what we actually care about are these things. These are called field effect transistors, or FETs, and they are what we want to talk about today. These little guys are the reason for the entire modern world. When Intel released its first commercial microprocessor, the 4004, back in 1971, they could fit about 2,000 of these little transistors into one of these silicon dies. Nowadays, we can fit over 2 billion. For most of the 50 years or so that we've been building computers based on integrated circuits, growth and improvement has been exponential. Every couple years, we were doubling the number of transistors, while at the same time doubling the speed at which we could switch those transistors, what's called switching speed. But about 15 years ago, cracks started to show. In about 2005, we largely gave up on trying to make transistors switch faster. 10 years ago, if you went to buy a new CPU, it typically switched at about 2 to 4 gigahertz. If you go to a store today, it's pretty much the same. The reason for this is because switching the state of a transistor takes energy. So the more you do that a second, the higher the switching speed, the more power you must consume, and the more power you consume, the more heat you generate. And heat is bad for computer chips. And yet, consumer electronics have to sit in a bath of air at room temperature. Given that constraint, there's only so much heat you can pull out in a second. And in about 2005, we hit that limit. Of course, for things like expensive corporate computers like servers and data centers, we can do more exotic cooling things like cooling with water or even liquid nitrogen, but that is hella expensive and out of reach for the price range of typical consumers, so power consumption has gone flat. And yet computers have still been getting faster since then, and that's because even though switching transistors faster must increase their power consumption, but making them smaller actually decreases it. Using something called Dennard's scaling rules to guide us, we've been very clever in exactly how we've shrunk our transistors year on year. We've been able to do it in a way such that their power consumption shrinks right in step with their size. Thus, we've been able to keep the total power used per chip fixed. Because of this, even though we hit this heating limit a decade ago, we could still force more and more transistors into our integrated circuits. This brings us to the point of the video. What I want to talk about today is the reason why, very soon, in a matter of years, this has to end. Specifically, I want to talk about two physical limits we are about to hit in our computing technology that stand to inevitably disrupt this golden age of progress in computing. And these limits come from the fundamentals of physics themselves. So let's talk about these field effect transistors. Conceptually, we can think of them kind of like water valves that can control the flow of electrical currents and be shut on and off. But let me represent this notion of switching in sort of a funny, abstract way. On the left, let's imagine we have a huge reservoir of electrons, which we call the source. And these electrons are just itching to move across the so-called channel and get to the region on the right, which we call the drain. So if there is nothing stopping them, electrons move from the source to the drain, and there's an electrical current through the channel of the transistor. The way I'd like for us to think of or conceptualize this reservoir of electrons is in terms of how many electrons do I have with a given amount of energy. I want us to be able to think in terms of a graph like, say, this. We call a graph like this the energy distribution of the electrons in the source. Now, energy is directly related to the amount of motion or speed something like an electron has. So looking at a graph like this, I can see in this example that most electrons have about this much energy or speed, but some will have a bit less. And what is very, very important to us is that if we think of higher and higher energies or speeds, you find that there are less and less electrons that have that amount of energy or speed. People often call this the high energy exponential tail, and they call the electrons that make it up hot carriers or hot electrons, because they have more energy than the equilibrium average. Now, the reason we want to think of things in this sort of funny way in terms of number of electrons with a given amount of energy is because it makes it very easy and simple to understand the physics of how our little switch is being turned on and off. What I mean by this is that, as the name implies, in a field effect transistor, what is stopping electrons from crossing the channel when the valve is closed is an electric field. This electric field is controlled by what is called the gate, which is the third electrical contact beyond the source and drain. So a transistor has three leads: source, drain, and gate. And in a nutshell, when there is no voltage applied to the gate, this electric field just exists naturally and the transistor is off. When a voltage is applied to the gate, this induces a reduction in the strength of this electric field and the device is turned on. So the electric field is actually there naturally, and it actually requires external work by applying a voltage on the gate to reduce that field. Now, in terms of a mental picture, you can just think of this as an electric field that, because electrons have electrical charge, just pushes or repulses them out of the channel region. You can totally think of things like that. But another way of thinking of this is in terms of potential energy. When the transistor is off, the channel region sits at a higher potential energy than the source region. You can literally think of this like its altitude is raised, so there's like a big hill blocking the middle of the channel. And this is actually a pretty good analogy, because in terms of physics, a hill is just a region of higher gravitational potential energy, where here we have an area that has higher electrical potential energy. So the analogy is actually pretty direct. So there's this big honking hill separating the source and drain, and in our source, we have all our electrons with a certain distribution of speeds. Given this, it's very easy to figure out the effects this hill will have on the flow through the channel. If we imagine the potential energy when the transistor is on, and there is no hill, falls here on our energy distribution plot, and the potential energy when the transistor is closed, and there is an electrical potential hill, is here, then the physics is simple. All electrons that have less energy than this are blocked, and they can't make it over the hill. They don't have enough speed to make it to the top, and they just roll some of the way up before running out of speed and then roll back down. Whereas all electrons up here in our high energy tail can make it over the hill. The hill doesn't stop them. So we see then that field effect transistors, by their very nature, are not perfect switches or valves. When you apply a voltage across the channel, and the transistor is on, and the gate is open, a certain electrical current will flow. We call this the on current. However, when the transistor is off, the so-called hot carriers or hot electrons can still flow. So there is a certain unwanted but unavoidable off current. Now, a natural question you might have then is, why don't we just make the barrier higher? Well, hold on to that question for now. We'll revisit that again. But okay, so now that we have an idea of what is going on inside a field effect transistor or FET, what I want to discuss are two crucial, paradigm-disrupting, fundamental issues that are bringing the progress and development of computing technology to an end. The first of these is an issue that has already, for the last 5 years or so, been throttling advancement and has forced newer and newer chips to find increasingly exotic and expensive workarounds year after year. For over 50 years, we've essentially been making incremental improvements and downsizing the same type of field effect transistor, a so-called metal oxide semiconductor design, or MOSFET. However, from about 2012 to 2020, we'll have changed to a new device not once, but twice. Think about that. One device stuck with us for 50 years, but now we've had to reinvent the wheel twice in a decade. So what is this issue that has forced this? Well, it relates to the quantum mechanical behavior of electrons. It's a quantum effect that up till now hadn't been such an issue because devices were so much bigger. Well, actually that's not entirely true. We've actually been fighting this issue since the 1990s, but things have finally hit a wall, and we started retiring our old friend the MOSFET in 2012. The specific issue relates to what is called quantum tunneling, and because of it, we are, in a nutshell, losing our ability to close the channel. This tunneling is causing the off currents of transistors to creep up, up, up as we shrink them. Now, I'll likely be doing a more complete look at what quantum tunneling is and how it both positively and negatively affects technology in a future video. But all we really need to understand about it here is that quantum mechanics says that electrons aren't particles but wavy things. And when wavy things hit a boundary or barrier that they don't have enough energy to overcome that reflects them, they actually bleed a bit past this boundary. Because of this tendency of waves to bleed into a so-called energetically forbidden region, if the barrier region is physically actually quite thin, they can actually leach through to the other side and just keep on trucking. Now, to be clear, the fact that waves do this is not something new about quantum mechanics. It's a general thing that waves do. Take a look at something like a Glan-Foucault prism, for example, which we fully understood and have been using for like half a century before we ever learned anything about quantum physics. Rather, the big quantum leap here is that electrons, which we traditionally think of as billiard ball-y type particles, are in fact also wavy things. And so they do these things that waves do. So what does that mean for our transistor? Well, as we've been cramming more and more transistors onto a single chip and making them smaller and smaller and smaller, the physical length of this channel has also been shrinking and shrinking. And to put it simply, we're at the point that things are so thin that when the transistor is off and the potential energy hill or barrier is up, even these carriers that don't have enough energy to overpass it can still make it to the other side through quantum tunneling. They're starting to leach to the barrier, and it's hard to stop that because, hey, quantum mechanics says electrons gonna tunnel. This has two big negative effects. Firstly, when you apply a voltage across a circuit and current flows, power is consumed and heat is generated. So remember before we talked about how because we can't pull heat out anymore, we had to stop increasing the switching speed because switching faster leads to greater power consumption. But then we also said that because the static power consumption per transistor can be decreased with size, that we can make more transistors that are smaller without increasing the power consumption. And that's why we've been able to keep this going while this has flattened. Well, because of this unavoidable off current, transistors also leach power even when they're off. However, once it was manageable and largely remained fixed as we downscaled and downscaled. But now, as we make transistors smaller, the channel barrier region gets thinner, and this power consumption has started going up. Power consumption, because of parasitic quantum tunneling, is starting to be the dominant source of power consumption in new chips, rather than the switching speed. To combat this, and to stop this curve from flattening as well, the semiconductor industry has been taking some bold and very expensive steps. As we said, in 2012 they adopted a new type of device, which is called a FinFET. This was a change that took about 10 years of research and development to get in line, but now many modern chips are based on FinFETs. So then things are fine, right? We spent 10 years getting this going, but it fixed it, right? Nope. Companies have already announced that within the next few years, parasitic leakage, even in FinFETs, will be too high. And they've already started shifting again to what is called a gate-all-around field effect transistor, or GAFET. So will these GAFETs fix this issue? No, they will cost an extraordinarily large amount of research and development to implement, and only buy us a few more years. So what do we do after that? We don't know. In fact, for almost 30 years, all semiconductor companies got together every year to hammer out a roadmap for where their technology was going in the future. They called this the International Technology Roadmap for Semiconductors, or ITRS. Well, in 2016, after doing it for 30 years, they pulled the plug on the ITRS. They've given up on the roadmap. The point is that this issue is fundamental. You can't stop an electron from quantum tunneling, and it's only going to get worse as we continue to downscale. But guess what? This issue isn't even the worst of it. Let's now talk about our second big fundamental limit, and this one is a doozy, and it's called Boltzmann's tyranny. To see what the big issue is, we need to ask ourselves what the theoretical and fundamental limits are for everything going on in one of these transistors. The first thing we need to look at is the relationship between the voltage we apply at the gate and the amount that the height of this potential barrier is lowered as a result. Applying a voltage actually means you're creating a certain difference in electrical potential energy between 2 points. That's why the terms voltage and potential difference are basically synonymous. However, the gate and channel are in physically different places, separated by a layer of insulating material, and the effectiveness at which the voltage change at the gate results in a potential energy reduction of the barrier in the channel is typically less than 1-to-1. The strength of this relationship between the gate's voltage and the channel barrier potential energy drop is called the capacitance of the gate, and in any real device it's not infinite. But since we're interested in theoretical limits, let's just say it is. If it were infinite, then applying say 5 volts to the gates would lower the potential energy barrier by 5 electron volts. You'd have a 1-to-1-ness. So that's the best we could ever do, so let's assume that. The second thing we need to think about is what determines the supply or distribution of electrons that are available to move through the channel. There are actually a few things that feed into this. The first is called the density of states. It's basically how many states exist for electrons in a given material that have a given energy. It's like the number of seats on the bus for electrons at each energy. And what is crucial to understand is this density of states function, the number of seats available, is a material property. It depends on what the transistor is made out of. But since we want to talk about fundamental limits, we don't want to make any assumptions about things like material properties. So let's just assume this too is infinite at all energies. There's just an infinite number of seats at all energies. Is this true for any real material? Not even remotely. But again, we're interested in fundamental limits. In fact, there's some other material-dependent stuff in here that I intentionally left vague. Let's just assume all that is perfect as well. Just give it the best, infinitely high values we can. So with this attitude of making everything the best it could ever be, we finally come to this part. This is called the probability distribution. If this is the number of states available at a given energy, then this is the chance or probability of one of those states at that energy being occupied by an electron. It's the chance a given seat is filled. And you can see then how these together tell us the number of electrons at each energy. You just multiply how many states are available by the chance of such a state being filled, and you get the number of electrons. But this is the key point. This probability distribution must follow what is called a Boltzmann distribution. This is where the word Boltzmann and Boltzmann's tyranny comes from. But this distribution isn't a material property. The Boltzmann distribution comes straight from the laws of thermodynamics themselves. We don't control this, and there is no way we could control this. This just comes from how heat and thermodynamics works. And because no matter what we do with these material properties, it will still be there, it puts a limit on how much we can shrink a transistor. To see why, let's revisit this question of why we don't make this potential barrier as high as possible. Well, we now understand that if we wanted to do that, we'd have to make the gate voltage as high as possible. This would be bad, and it's because of power consumption and heat dissipation. Remember when we said that we're at a wall with heat extraction? We can't cool chips any faster, so we can't have chips use any more power because power consumed equals heat generated. And we saw that the more you switch a transistor each second, the more power it uses, which is called the dynamic power consumption. Well, the power cost every time you switch also dramatically increases with the so-called supply voltage, which determines the voltage at the gate. So the higher the barrier, the more power is used when you switch the transistor. In fact, increasing the supply voltage also makes the power consumed by our leakage current due to quantum tunneling higher as well. So like I said, increasing this would be bad. We in fact want it as low as possible. However, at the end of the day, the whole reason we're doing this is because this is supposed to be a switch. It has a 0 or 1 state that needs to be clearly discernible. Specifically, the on current must be much greater than the off current. Just to give you an idea of a number, a typical value we like is about a factor of 1,000,000 or higher. So when no voltage is applied, our little potential energy barrier is up, and there is a certain off current. We then apply a certain number of volts of voltage at the gate, which lowers this barrier. Since we're assuming things are perfect, it's lowered by the exact same amounts. This gives us our on current. We want this on current to be much, much higher than the off current, but at the same time, we also want this voltage to be as small as possible. The question is then, how well can we simultaneously satisfy these wants? And the answer to that is Boltzmann's tyranny. Boltzmann's tyranny is actually just a number. It's 60 millivolts per decade. A decade is a power of 10. So, for example, if we want the on current to be 1,000,000 times higher than the off current, then, well, 1,000,000 is 6 powers of 10, or 6 decades. So Boltzmann's tyranny says that if we want the on current to be 1,000,000 times higher than the off current, this supply voltage cannot ever be lower than 0.36 volts. Ever. Where this number is coming from is this Boltzmann distribution. We assumed all the material properties like density of states were infinite. We assumed the relationship between the applied voltage and the barrier lowering was infinitely good. But the only thing we can't ever change is this, because it comes from the laws of thermodynamics themselves. And this alone puts an upper limit on how much current can be increased by raising a voltage. Put another way, thermodynamics puts a fundamental limit to how abruptly a field effect transistor can turn on with increasing voltage. And this limit is totally independent of the material used or the design of the FET. Based on nothing but this Boltzmann distribution, you need to lower this barrier by 60 millivolts if you want the current flow to increase by a factor of 10. And we are literally just a few years from hitting a point where we need supply voltages to drop below this point if we want to keep power consumption constant. And when we hit this limit, it will be impossible to make transistors smaller without also increasing the heat they produce. So okay, in this video, we learned about how quantum tunneling and Boltzmann's tyranny represent an inevitable disruption of future progress in making better computers. Now, those two issues are not the only key issues. There are a couple others, but this video is already the longest I've ever made, so I thought I'd keep it to 2. But before I sign off, I want to check people's opinions about something. I'm sure many of you, after having seen this video, may be yelling at your screen at me about, say, non-traditional computing paradigms, like quantum computers or neuromorphic computing, or non-traditional field effect transistor devices like negative capacitance FETs or tunneling FETs, or about non-traditional computing architectures like spintronics or optical computers, or what have you. You may want to talk about how these emerging technologies will swoop in to save us from the situation we're in. However, I think in order to understand the role these things may or may not play in circumventing this upcoming disruption requires a broader discussion of the computing industry and its business and economics. In other words, to really fully see the pickle we're in, we need to look at things not just from the perspective of a physicist, but also as a technologist. So if we want to talk about if quantum computers or graphene can or can't be our savior, we'd have to talk about some of the brass tacks of the economic and manufacturing side of the issue. But this is a physics channel, and I am a physicist, not a technologist. And so such a video would both be different from the physics videos I've made previously, and would also necessarily be injected with some amount of my own non-expert opinion about the industry, even though I do my best to look at the different sides of things. So my question is, do people want such a follow-up video that looks at the future of computing from a technologist's perspective, or should I just continue on with another physics one? Let me know in the comments if you have any opinion about this. Otherwise, I'll just decide for myself. But anyways, hope you enjoyed the video. See you next time. Have a good one.